Welcome to the Deep Dive, where we take your source material, the research papers, the notes, the insights, and synthesize it into immediate knowledge. Our mission today, well, it's about a problem that is haunting pretty much every company trying to leverage AI. And that's the huge gap between the promise of large language model agents and their, let's face it, messy real-world performance.
It really is the Achilles heel of modern AI deployment, isn't it? We've all seen these incredible demos, LLM agents automating software development or customer support. But then you go to implement them and they constantly underperform.
And why is that?
It comes down to fragile, suboptimal configurations. It's not the LLM's brain that's the problem, it's the instruction manual we're giving it.
If you're out there building these systems, you know this pain. You try to tweak the system prompt, you adjust a tool definition, maybe you fiddle with a token limit. The research says this can take weeks of manual refinement, and you end up with something brittle that just breaks the second the task changes a little.
It's labor-intensive, it's not reproducible, and it just doesn't scale. And that, right there, is why we're looking at Artemis. It's a solution designed to just automate that pain away.
Okay, so what is it?
Think of it as a no-code evolutionary optimization platform. So instead of a human tuning things by hand, it treats the whole LLM agent, the prompt, the tools, the parameters, everything as a black box.
Yeah.
And it uses these sophisticated algorithms to jointly tune the entire configuration until performance is maximized.
Okay, let's unpack this, because the power here seems immense. We're going to dive into how this platform gets some truly staggering gains, and I do mean staggering. We're talking a 22% jump in accuracy on math problems, a 13.6% increase in acceptance rates on coding challenges,
And even a 36.9% cost reduction.
a jaw-dropping 36.9% cost reduction.
Yeah.
And here's the crucial part. It does all this without you needing to become some kind of expert in evolutionary algorithms.
It basically fixes a configuration crisis that, human-driven tuning just can't solve.
So let's drill down into that crisis. Why is configuring these agents so hard? It feels like it should just be about writing a really good prompt.
You'd think so, but it's much, much deeper than that. A modern LLM agent is a whole multi-component pipeline. You've got the main system prompt, maybe some few-shot examples. You've got detailed tool documentation, retry strategies, and then all these continuous parameters like temperature or top-up.
And when you put all of that together,
You end up with a configuration space that's incredibly high-dimensional, and this is the key, heterogeneous.
okay, stop right there. High dimensional and heterogeneous. Break that down for us.
Sure, think of it this way. The dimensions are just all the things you can change, right? The words in the prompt, the choice of a tool, the value for temperature. You're mixing natural language, which is infinite, with discrete choices like tool A or tool B, and then continuous numbers.
So it's a mix of different data types that are all tangled together.
Exactly, a mess of different data types that all interact.
And that messy, mixed up space is why the traditional optimization methods, the ones that have powered machine learning for years, they just fail here.
Oh, they're dead on arrival. Take gradient descent, the workhorse of deep learning. It requires your objective function, your performance score, to be differentiable. It needs to tell you not just, that was bad, but you're bad in this exact direction, so adjust parameter x by plus 0.01.
But with an LLM agent, you just get a pass or fail.
Yeah.
Right. It either solved the problem or it didn't. There's no gradient.
Precisely. It's non-differentiable. It's like trying to find the highest point in a valley while you're blindfolded. If your last step went up or down, but you have no idea which direction is the best one to go next.
You only know the result, not the path.
Exactly. You only know the fitness of one configuration. And on top of that, you have these non-trivial component interactions. You might optimize the prompt in isolation, but that could actually make the agent use a tool wrong. You need to look at everything at once.
And then there's the huge problem of cost, the speed bump.
The evaluation cost is prohibitive. Running just one single candidate configuration, a full benchmark run, can take minutes, sometimes hours of compute and API calls.
So forget about trying everything.
Exhaustive search, grid search, even random sampling is completely out of the question. You need an incredibly smart system to find that needle in the haystack without checking every single piece of hay.
Okay, so if traditional optimization is out, what about the other things people are trying? Like isolated prompt tuning, methods like APE.
Those systems can be useful, but they miss those crucial interdependencies. APE might find you a great prompt, but it's assuming your tools and parameters are already perfect,
Which they never are.
which they're almost never.
Yeah.
Artemis is designed as this unified end-to-end framework. It's agnostic to the agent implementation. It doesn't care if you built it with Crew AI or LangChain or something totally custom. It treats the whole pipeline as a black box and optimizes all the components together. That unified approach, that's the real key.
All right, now that we understand the impossible problem it solves, let's get into the mechanics. How does Artemis actually evolve intelligence? I hear it has roots in earlier genetic algorithms for code.
It does, yeah. It traces back to the Turing AI intelligence engine. But the main priority here is accessibility. For anyone building these systems, the interface is genuinely no code. You don't write complex algorithms, you just upload your benchmark script, and then you define your goals in natural language. Something like maximize accuracy while reducing API calls. The platform just takes it from there.
That accessibility is huge.
Okay.
So walk us through it. How does it even know what to optimize in my code in the first place?
That's the first step, project setup and component discovery. The platform automatically scans your entire code base. It doesn't need you to manually point to files or add annotations. It uses semantic search to automatically find all the optimizable targets. Every system prompt, every tool description, every parameter. It just maps that whole complicated space on its own.
So find its own targets that must save days of developer time.
Absolutely. So once that space is mapped, it deploys its optimization strategies. And there are two complementary ones. For individual components, like, say, just refining the wording of a single prompt, it uses local optimization with genetic algorithms.
Hold on, semantically aware mutation. Does that mean the AI it's intelligently rewriting its own instructions like a skilled editor, not just changing random words?
Precisely. This isn't just scrambling the text. The system uses an LLM ensemble to perform intelligent changes. It understands the context, it maintains grammar, and it explores meaningful variations. It's like it's taking the best traits of successful prompts and breeding them to create a superior one.
So it's teaching itself better phrasing.
Yes. And then for finding synergy between different components, like the perfect combination of a prompt and a tool parameter, it switches to global optimization using Bayesian optimization. That method is just brilliant for finding those effective configurations when different parts interact strongly.
That makes a lot of sense. Local fixes from the intelligent editor, global fixes from the system that finds the perfect cocktail mix. But what about that cost problem? How does it manage potentially hundreds of hours of compute time?
Right, that's where the secret sauce is. Hierarchical evaluation. This is the key to managing costs.
Okay, it sounds smart.
It is. Think of it like a very efficient hiring process. You use cheap, fast evaluators first, like a simple LLM-based score or static analysis, to filter out all the obviously bad candidates right away.
So you get rid of the no-hopers first.
Exactly. Only the most promising, the highest scoring configurations move on to the expensive, slow evaluators, which is the full benchmark execution. You're letting a cheap filter eliminate 90% of the junk before the expensive process even starts.
And the result of all this is that the agent moves beyond these generic instructions to something really precise. You had a great example of this from the source material. What did the prompt look like before?
Oh, it was typically vague. The starting prompt for this competitive programming agent was basically, generate a solution for the given problem, consider edge cases. Just general advice.
And what did Artemis turn that into?
It evolved it into something profoundly structured, a multi-step methodology. It became decompose the problem into subcomponents. 1, identify input-output patterns. 2, detect the algorithmic category. 3, enumerate edge cases explicitly.
Wow.
4, implement with clear variable naming and modular functions. That shift from a vague suggestion to a systematic methodology is what drives these huge performance gains.
That clarity is the tangible result.
Yeah.
Okay, let's talk proof points, because the results across these 4 real-world agents really highlight the power of this. We'll start in a really tough domain, algorithmic reasoning.
Right. So first we look at the ALE agent, which tackles competitive programming problems on the AtCoder heuristic contest benchmark. This is complex, multi-step reasoning.
And the prompt optimization alone got a 13.6% improvement in the acceptance rate, jumping from 66% to 75%. In a field where experts fight for a single percentage point, that's transformative.
It is. It really confirms how much prompt clarity matters for these hard reasoning tasks. But we have to be honest, this one required a lot of compute, about 411 hours. That's the trade-off. But that optimized configuration is now durable and far more effective forever.
Okay, moving to a different challenge.
Yeah.
The mini SWE agent. which does code performance optimization. This is less about pure logic and more about finding bottlenecks and understanding complexity.
And here, Artemis delivered a statistically significant 10.1% performance gain. And what's fascinating is how it changed the agent's strategy. It moved it away from just general improvements and toward bottleneck-driven optimization. It did that by explicitly demanding complexity analysis and using techniques like vectorization.
So it taught the agent how to be a more specialized performance engineer. Do you have a specific example?
Absolutely. Within that benchmark, we saw a 7.2% gain for optimizing the request library and a 1.8% gain for the Astropy project. The system learned to apply the right specialized techniques, not just write cleaner code.
That move from general to systematic seems to be the pattern. Now let's talk money. Let's shift from pure performance to cost with the Crew AI agent on the Math Odyssey benchmark. This one was already pretty well-tuned.
Exactly. The baseline accuracy was already decent, around 54.5%, so there wasn't a huge ceiling for improvement there. But this is where multi-objective optimization really shines. We told Artemis to keep accuracy roughly stable, but optimize purely for cost.
And the result was that dramatic saving.
A dramatic 36.9% decrease in token cost, which is highly significant. It shows the platform can find these savings by, making prompts more brief, cutting out unnecessary steps, and setting more efficient token limits.
If your system runs millions of times a month, that is a game-changing win for the budget. A third of the cost for the same accuracy. That's something every CFO should hear.
And finally, we saw it work with smaller open source models, which is crucial for accessibility. The MathTales teacher agent, using the Qwen 2.57b model, was working on primary school math problems.
And smaller models notoriously struggle with things like getting stuck in loops or just making confident but wrong calculations.
They do. But Artemis delivered a massive 22% accuracy improvement on the GSM 8K benchmark. The optimized prompt introduced these explicit self-verification steps. It forced the agent to decompose the problem and check its own work.
So it basically patched the common failure modes of that smaller model.
Exactly. It validates that this works on both the commercial giants and the smaller open source models that more people can actually use.
So if we synthesize all of this, what's the main lesson for organizations that want to deploy this kind of tech?
The key insight, I think, is that your success really depends on the quality of your starting point, your initial configuration. The agents that started with poorly tuned, vague prompts, they saw the biggest gains, sometimes 15, 20%.
And if an agent's already performing well?
If it's already near optimal on one metric, like the Crew AI's accuracy, then you should strategically target a secondary metric, like cost or latency. It's brilliant at finding where the most potential energy is stored in the system.
It finds the low-hanging fruit and then structures the whole system around efficiency. But we have to come back to the trade-off, the cost. I mean, the ALE agent took over 670 total hours. That's a big investment.
It is. And that high computational cost and the risk of overfitting, you have to weigh that against the deployment lifetime.
Yeah.
If that performance gain is critical and the agent will run for years, then that upfront cost is absolutely justified.
But it's not for small one-off tasks.
No. It's for high-leverage, complex pipelines where that initial investment pays off hundreds or thousands of times over.
It sounds like it's best used when you have clear metrics and you suspect that your current human-tuned setup is tragically suboptimal.
Which, frankly, is the state of a lot of deployed LLM agents today.
So this is the bridge.
It is. Automated semantic optimization is rapidly closing that gap between the theoretical potential of LLM agents and their actual practical, robust performance in the real world.
It's moving beyond just building a better architecture like Tree of Thoughts or React.
The next stage is building automated systems that teach those architectures how to use themselves in the best possible way, finding those perfect configurations no human could ever discover manually.
So what does this all mean? We've seen profound performance gains, we've seen cost savings that could transform a business, and we have a technology that makes this accessible to engineers, not just optimization specialists.
It means we're entering an era of self-improving agents. The performance ceiling just got raised, substantially.
We saw Artemis teach an agent how to optimize code, how to self-verify math, how to manage its own costs. So here's a thought I want to leave you with. If an AI can use these algorithms to intelligently rewrite its own instructions for better and cheaper performance, how long until we stop needing human engineers to write the original instructions at all, leaving the entire creation and tuning process to the agents themselves? Something to think about as you figure out where your next optimization budget is going. That's all the time we have for this deep dive.